Let's now talk about the second example for recursion, which is the famous Fibonacci sequence problem. And for those of you who haven't seen the problem before, let's now take a look quickly. So this is an infinite sequence of Fibonacci numbers, basically, right? These are just the first few numbers in the sequence, and the sequence itself is simply just infinite. Can you identify the pattern that's actually in this sequence here? Right? Once you identify it, you're almost done with deriving the recursive definition for that. Let's now let you pause the video and think about it. All right, assuming that you thought about it and hopefully you derived the pattern. Let's now take a look. Okay, so this is part of the Fibonacci sequence over here. I just name it F over here for Fibonacci. Okay, you can see the first element there is 1. Second number there is 1, right? So these are always fixed. And then starting from the third number over here, you can see 2 is equal to 1 plus 1. And 3 is equal to 1 plus 2. And 5 over here is equal to 2 plus 3, and etc. And one more. 89 over here is equal to 34 plus 55. So it seems like the pattern is as follows. Starting from the third number, in which case you got at least 2 earlier numbers. The number over here is simply the sum of the earlier 2 numbers in the sequence, and it's going to be the pattern. All right. So let me just visually highlight. For example, if I want to calculate 34 over here, and it's simply going to be the sum for 13 and also 21, and you can do the same calculation for every number in the sequence. Let's now talk about the recursive definition. So what's the base cases? Okay, let's say base cases. So base cases should be those problem size where we can know the solution right away, right? It seems like 1 and 1 over here are the base cases because those are the one. Well, for example, you can see here 1 does not have the earlier 2 numbers for us to calculate, and also 1 does, has the earlier number but not the second earlier number over here for us to calculate. So these two are something that we can assume exist right away, right? So the notation we're going to use will be Fibonacci sequence. The first number is going to be just 1. And for the second number in the sequence is also going to be 1. So these are the 2 base cases. So if you're asked to calculate what's F1, well, you can return 1 right away. What's the value for F2? It will be 1 right away. So what about recursive cases? Okay, let's now put it. Let's say recursive cases over here. Okay, let's now just see the example I put over here, right? So which is this number? This number over here, you can see 1, 2, 3, 4, 5, 6, 7, 8, 9. So this number over here is the 9th number in the sequence. So this will be F9, which is equal to exactly the 2 previous number and added up together. So this will be F7 and also F8, right? You can see F9 over here. F9 is simply equal to F7 plus F9. F7 plus F8. Right? And now, how can we derive this generally? Okay, well, you can pretty much know what to do. Here, you can see Fn over here, and we assuming that n is actually strictly larger than 2. Because if n is less than or equal to 2, in that case, we can simply use F1 and F2. So these are the base cases. So we got to make this assumption over here. If n is strictly larger than 2, what would that be? Well, it would simply be the number before that, which would be Fn minus 1 plus the next earlier number, which will be n minus 2. So this will be the recursive definition. And it is indeed recursive because we are talking about the same Fibonacci sequence number problem, right? But the problem size are actually strictly smaller. You can see this is the first recursive call over here. And this is strictly smaller. Strictly smaller than the original problem size, which is n. And also n minus 2 over here is also strictly smaller than n. So we are basically making 2 recursive call over here, and then each one of them is making on the problem size that's actually strictly smaller. All right. Let me just make one more note, and then we can go back to the slide and see how the code should be written. Okay. So this part over here is really important to know that this can be solved recursively by 2 recursive call. Okay, and let me just highlight it. So 2 recursive call, number 1 and number 2. All right, hopefully that makes sense to you about the recursive definition. If you look at the recursive definition I've included over here, that's exactly what I just described. But you should really know the derivation process. I think that's more valuable for you to understand. What about the Java code? Let's take a look at right away. Given the recursive definition for the Fibonacci sequence number, right? So we got 2 base cases and 1 recursive cases. But the recursive case is going to make 2 recursive calls, right? So now let's say we declare some method over here, Fibonacci, just a fib, and also some number. You can think about n corresponds to the n over here. So we got 2 base cases. In the case of 1, in the case of 2, both will actually give you the result, just 1. And the recursive case over here will just corresponding to Fibonacci of n-1 and also Fibonacci of n-2. Right? So these are the 2 recursive cases. And it should be rather straightforward for you to see the correspondence between the mathematical recursive definition and the implementation in Java, right? So I would say to really, whenever you're given a problem to solve recursively, first of all, think about what's really the recursive definition on the paper. And then it should be rather straightforward for you to translate into Java, right? Or any other language. Any language that will support functions or methods should definitely allow recursion. So you really want to learn about the more general problem-solving technique. That's more important. All right, so what's really left about Fibonacci numbers is really to see how we can trace recursive call using the call stack. So that's something I would like to do. Let's now try the Fibonacci number of 4. Like in the case of factorial calculation, I would like to show you 2 ways of tracing this. One would be using the very precise runtime stack technique. The other one would be just using like a tree structure to actually trace the recursive call in a higher level. Right? We're going to see both at the same time. Okay, let me start with the higher level one, just to understand what's going to be the roadmap for tracing the call stack. Both ways should be consistent with each other. Okay, so we're going to do Fibonacci of 4, and just I assume that you know very well about the structure for the methods. We got 2 base cases, and also we got 1 single recursive case, which makes 2 separate recursive calls. Right, that's really important to remember. Okay, let's now start with the high level, like a tree structure diagram. Okay. Let's say this. Okay, let's say I want to execute Fibonacci of 4 to begin with, right? Itself is going to reach the recursive case because 4 is way too large. It's not really reaching the base case just yet. So it's going to be boiled down into the execution of Fibonacci of -1, -2, right? So it's going to be Fibonacci of 3 and also Fibonacci of, Fibonacci of 2. And Fibonacci of 3 over here is going to boil down into Fibonacci of 2 and also Fibonacci of 1. So now you can see at the bottom here, 2, 1, and also 2. They're all base cases, right? That's what's going to happen. To be more precise, we will start with Fibonacci of 4 over here. Oh, let me just use a different color. How about this? We will start with Fibonacci of 4, and then itself is going to be suspended, and then we do the recursive call calculation. We're going to do Fibonacci of 3. And notice one thing here. Before this result is available, we cannot really calculate the right-hand side because the order of evaluation at the runtime is going to be from left to right. And in order for the right-hand side calculation to really start, you must make sure the left-hand side is completely terminated and also returned. So that means we cannot really evaluate Fibonacci of 2 until this entire subtree, this entire branch of the calculation is terminated, right? It's really important to see that, okay? And in order to calculate Fibonacci of 3, we're going to boil down into 2 parts. One is Fibonacci of 2 over here, and Fibonacci of 2 is actually a base case. That's good. So once it is returned, we're going to calculate Fibonacci of 1 over here, right? So once we know the result for these two, we can combine them to calculate Fibonacci of 3. And once this one is is actually known to us, we can actually move to the right about Fibonacci 2, which is also a base case. And we're going to calculate this one as well. Let me use red over here. And once we calculate Fibonacci of 2, once it returns, we can calculate these two together. And once we know these, we can go back to Fibonacci of 4. And that one there is going to be the result for the summation of these two. All right, so that's a very high level tracing, but I would suggest that we also do the very precise tracing to see exactly what's going to happen at a runtime stack. So that's what we should do, right? So the reason I put some colors over here, you can see we got orange, we got blue, we got red, we got pink, we got purple, is because when I actually put the recursive call onto the stack, I will try to follow the color convention so you can see the correspondence between the two mechanism, right? There's a reason for that. All right, let's now do it. I'm going to do it together with you, but I would suggest you also try to do the exercise yourself as well, maybe after you have watched my demonstration. And then in the slides, I actually included another even more complicated tracing, which will be Fibonacci of 5. You should also try it yourself, all right? If you got any trouble tracing it, you can let me know. We can do it together again. Let's now take a look. I'm going to start with Fibonacci of 4, right? That's what I will start with. So I'm going to put that onto the stack. So Fibonacci of 4 over here, okay? So we know that it's not actually the base case over here because 4 is not equal to 1, not equal to 2. So we're going to execute the result for the first time over here. I mean, we're going to execute the recursive case for the first time. And that one there is actually going to be boiled down into 2 execution. It's going to be Fibonacci of 3, okay? So it's going to be Fibonacci of 3 over here, and also plus. And it's going to be Fibonacci of 2. Fibonacci of 2. Right? You can see so far I try to be very consistent with the colors I use, right? 3 and 2 over here. Which one are we going to execute first? The runtime evaluation in any programming language is going to be from left to right. So for this plus binary operator, we're going to evaluate this completely and terminates and return before we can get to this part. So that means we're going to push this onto the stack over here. That's what we'll do. So I'm going to do Fibonacci 3 now. So I'm going to put Fibonacci of 3 over here. And then I'm going to execute this Fibonacci method for the second time. And by the way, the first time was actually when we first started with 4, right? Just don't forget. All right, so Fibonacci of 3, and also 3 is not equal to 1, it's not equal to 2, so we are also going to bypass the 2 base cases. And we're going to execute this recursive case for the second time. And now in this case, you can see we're now here. That one there is going to be further split into 2 recursive call, which will be the following. So it's going to be Fibonacci of 2 over here, and plus Fibonacci of 1. Fibonacci of 1. Right, over here you can see corresponding to these two over here. And again, we're going to do evaluation from left to right. Right, left. So we're going to finish this, terminates and return before we can execute this. So that means Fibonacci of 2 is going to be now pushed onto the stack. Let's now do it. So Fibonacci of 2 is now going to be pushed onto the stack over here. And then for that, we're going to invoke this method for the third time over here, right? And to really execute it, you can see 2 is actually matching this particular base case, right? So that means we're going to set the result to be 1, and then we're going to return the result. Okay, hopefully you're following so far. So that means Fibonacci of 2 is going to return a value of 1. Over here. So that one is going to return 1. Return 1. Okay. And more precisely, and what's going to be the next method to actually execute? It's going to be Fibonacci of 3, the top of the stack. And that one there was actually suspended because we were waiting for the result for Fibonacci of 2. And now we know it should be just 1. So what's going to happen is this part over here is just going to be 1. Right, you can think about this part here just replaced by 1, right? That's what we are doing. And then once it is 1, we can now move on to, it's not done yet. Okay, notice that the in order to really resume the execution for Fibonacci of 3, we have to also calculate the right hand side over here. So that means we're going to push this onto the stack, right? The purple one. So Fibonacci of 1, we're going to push that onto the stack over here, right? And that means we're going to execute this method for the 4th time, and then it's going to match this base case over here. The first base case is going to set the result to be 1, and then it's going to return the result over here, right? So it's going to terminate and return the result 1, and return 1 over here, right? So that means Fibonacci 1 here is going to be replaced by 1, and in the diagram here is also going to be replaced by 1. Now, in order to calculate Fibonacci of 3 over here, that's currently still being suspended, right? That's now the current execution point. In order to calculate this addition, do we have all the information needed? Indeed, we do. We got 1 here, that's returned from Fibonacci of 2. We got 1 here, that's returned from Fibonacci of 1. So 1 plus 1 is going to give us 2, right? It's going to be 2. Meaning that we're going to return from Fibonacci of 3 calculation and then return 2. Return 2 over here, okay? And once we, so that will be 2. So that'll be here, over here. So we got 2 over here, right? And notice that there's 2, just again, the return 2 over here is the result for calculating Fibonacci of 3. And how do we continue? We're going to look at what's the top of the stack. The top of the stack is actually Fibonacci of 4, right? It was suspended because we were waiting for the result for calculating Fibonacci of 3. But that one there already returned 2. Let's now replace the result. That one there returned actually 2. So that means this part we got 2, right? And then we will be able to continue with Fibonacci of 4 by going to the right operand for the addition. So now it should be Fibonacci of 2 that we should calculate, right? So now we should push that onto the stack. So what we will do is we're going to say this Fibonacci of 2 is going to be pushed onto the stack, Fibonacci of 2. In that case, we're going to execute this one more time, right? So this will be 1, 2, 3, 4, 5. 5th time we're executing the same method. And 2 indeed is a base case. So that means we're going to reach this particular base case one more time, and then we're going to set the result to be 1, and then return the result, right? So this will be simply returning 1. Return 1. Okay, meaning that this part here is going to be replaced by 1. And then, so this part here is going to be replaced by 1. So we will be able to now complete a calculation for Fibonacci of 4, right? Which will be the next one to execute. To calculate this, we need a result from Fibonacci of 3, which was returned already. And we also need a result for Fibonacci of 2, which was also returned already over here, right? So 2 plus 1 is going to give you actually 3. Okay, 3 over here. So that will be the result for Fibonacci of 4. In that case, that one is going to return, let's see, 2 plus 1, which will be 3, right? Return 3. So that's the final result. That's going to be returned, right? The final result is going to be, in both cases, it's going to be 3 and also 3 over here. That's the final result. If you look at that, Fibonacci of 4, 1, 2, 3, 4 is simply just 3 over here. I think it is simple enough, and also it does give us some new aspects about tracing the recursive call. Recursive call may be multiple. You may have multiple recursive calls that should be executed one after the other. So that's why I really want to trace this particular Fibonacci 4 very carefully with you, right? And I have been very, very careful about using the color over here, about starting with maybe orange and then followed by blue, pink, purple, and red for a reason, right? Just be careful about studying this particular tracing. As a challenging exercise for you, which I believe will be very beneficial, right? Let me show to you. So what about tracing Fibonacci of 5 over here? What's going to happen really? Okay, if you think about it, why don't I give you a little bit hints, and you should really do the call stack tracing yourself, right? Let's now try to do this. If I want to trace Fibonacci of 5, right? By definition, it's going to be Fibonacci of 4 plus Fibonacci of 3, right? Minus 1, minus 2. And for this one here, it's going to be Fibonacci of 3 plus Fibonacci of 2. And this one here also is not base case. Fibonacci of 2 plus Fibonacci of 1, right? So far we got base case, and base case. And this one here is not really base case, so we gotta go further for the recursive call. And this one here is going to be Fibonacci of 2 plus Fibonacci of 1. And now in this case, we got base case and also base case. So this will be the high level tracing for Fibonacci of 5. And can you actually go ahead and do it by yourself by grabbing a piece of paper and also have this code ready and do a similar tracing for Fibonacci of 5 using the runtime stack? I think that will be very beneficial for your understanding about recursive call or tracing recursive methods in general. I'll leave that exercise to you. All right. Let's now go back. Okay, so that's about the recursion. The two examples we did so far about factorial and also common errors about recursion and also the Fibonacci example. Hopefully that will give you enough intuition about what recursion really is. It appears to be magical, but it's really not once you actually consider what's really happening by using a call stack for tracing. All right, the next topic, we're going to see some series of examples using recursion on strings.